Okay, welcome to our lecture here in multiphysical simulation for magnetomechanical systems. So today we will discuss about the electromagnetic force and then the overall computational scheme. And the electromagnetic force can be decomposed into a Lorentz force, as shown here. You have, for example, a conductor where a current flows through, here described by the current density J, and it is within a magnetic field B. In this case, you see they are directly orthogonal, and you see when you take the cross product between the current density and the magnetic field intensity, we get the force density acting on this conductor here, carrying the conductivity J in the magnetic field B. So it is Newton per cubic meter. Integrating here over the domain omega will give us the total force, meaning integrating over this conductor here, giving us the total force in Newton. We know this current density, as generally written here, is the current density, for example, the impressed current density, but also any eddy current density being induced in the conductive body. So it could be, for example, a aluminum plate within a magnetic field, and it could be also due to moving. So we can also have here the term J, a moving body with velocity v being conductive with conductivity gamma cross product with B itself, where we again know that we express B by the curl of the magnetic vector potential. Okay, on the other hand, we have here the so-called pole forces. You see here a sketch where we have two regions, a region where we have permeability mu1, a region where we have permeability mu2. In this case, we will have here on the interface a pole force due to the change of the permeability, and you see it is directed here in this direction because the permeability mu1 is larger than mu2. We know the higher the permeability, the less energy we need, so we want to reduce the domain with the lower permeability. And actually we have here this fourth term where we see we have to integrate over the volume, and within the volume we have to evaluate the and taking the gradient of mu, which is clearly not as easy, especially as I just have told you, it occurs at this interface where the permeability changes, for example, between iron and air. But we can transform this volume integral in this so-called surface integral over the body, and there we have once to evaluate the normal component of the magnetic flux density and scale it here with the inverse of the permeabilities, and once the tangential component of the magnetic field intensity and scale it with the difference of the permeabilities. So you see, we really decompose the magnetic field quantities in a normal and tangential component, and I guess you know why we do this. We know that the normal component of P is continuous along interface, and the same holds true for the tangential, assuming no surface current density. So let's have a look how we can transform this general physical law, as shown here, for this pole force into this surface integral. For this, we cut out a small cylinder as shown here, where one part is still in omega 1, one part is still in omega 2, and clearly in order at the end to come up at the interface, we will let go the distance here from R1, position vector R1 to position vector R2 to 0. We assume here also that the cylinder is very small, so this cross section gamma, delta gamma is also very small, and the overall volume delta omega is small. So we compute for this small volume here the force, we call it delta F, and we know that we have to integrate here our volume force term, which is in our case, as you know, nothing else at h squared over 2 gradient of the permeability. Now, since we assume that over the cross section gamma, or let's say better say delta gamma, nothing changes, we just have to integrate from omega from R1 to R2, so over the head of the cylinder, our volume force. And here we assume now and plug in here this relation and see then that we have to integrate here. The factor 2 is now in front of the integral, which is clear. We have to integrate here now this term h squared gradient mu over the radius r here. Just we close the parenthesis. Okay, so what we also know is the following, that actually, and that is how the gradient can be also defined, that the total change of a scalar quantity is the same as the gradient of this quantity dot product with the direction dr. Now, our direction dr is here nothing else as the normal vector, so we can write it as the normal vector and dr is a scalar. Yeah, which means at the end, if we now put dr to the left-hand side, we get this relation that the total derivative of mu with respect to the direction r is the gradient of the permeability in normal direction, taking the scalar product with the normal. Now, and that we use, so we can now substitute our expression in a first step, as we see here. We introduce it here, and now we use this relation here. For this, we can use this relation, which means we have an integral over h squared and have then the total change of the permeability, d mu dr, integrate over dr. So this cancels out, and that means we just have to integrate over the permeability, and therefore we integrate here from mu1 to mu2, because at position R1 we have permeability mu1, we are in the subdomain omega1. At position R2 we have permeability mu2 at the position R2 in the subdomain omega2. Now, what we do is clearly a decomposition of the magnetic quantities, because it's not so easy to integrate here. As we see, we also have h squared, but when we integrate from mu1 to mu2, we know we have a continuity in the normal component of the magnetic flux density and the tangential component of the magnetic field intensity h. And that is why we decompose here h in its tangential vector and normal vector, and the same we do for p in this sense. And clearly what we always can use is this relation that p is equal to mu h, our constitutive equation. Okay, in doing so, we can rewrite h squared, which is nothing else as h as a vector dot product with h itself. So we rewrite it now in the normal component. So this is h normal, which we can express by p via our constitutive equation again. So we can clearly write this also, that Pn, since we assume an isotropic material behavior, is mu Hn. And since the tangential vector is orthogonal to the normal vector, all this mixed product ht in Pn over mu or ht in Pn over mu is 0. And what remains here is clearly just this part here, the normal component of the magnetic flux density over permeability squared, and here the tangential component of the magnetic field intensity squared. Now, let's plug this in here. And so, since Pn and Ht are constant over the interface where we integrate, we can put it in front of the integral, and once we have to integrate 1 over permeability squared over the permeability, and one we just have to integrate d mu. D mu gives us clearly evaluated at the limits as mu1 minus mu2. Remember, we have this minus, therefore we have mu1 minus mu2. And the same we have then here. The integration 1 over mu squared gives minus 1 over mu. With this minus, it cancels out. And so we have to evaluate and get 1 over mu2 minus 1 over mu1. Yeah, and that is then also what we get out. We know physically, but we also get it out. The force always points from a region with larger magnetic permeability to a region with smaller magnetic permeability. And we can rewrite this force density, which is now a force density on the surface, so it's Newton per square meter, by this value we just have seen how we compute it, and it's always pointing in normal direction. So it is a kind, mechanical speaking, a kind of a pressure force. Okay, the second possibility, how we can compute electromagnetic forces, and this is the principle of virtual displacement and includes both the Lorentz and pole force together. And we know what we have, that we get a virtual change in the energy when we apply a force on the body and move it virtually in a direction r. Due to the scalar product, we get out the force in this direction. So in 3D, we once have to do it in x, y, and z direction to get the x, y, and z component. And we know that we have here this energy we have to compute. The magnetic energy density over volume gives us the energy, and the energy density is 1/2 h in B, already assuming a linear material, but we will see that this is correct, our assumption. So from the point of view already finite elements, what we have to do is when we have such a body, we look at the surrounding finite elements of this body, let move the nodes on the surface of the body and fix the nodes already here on this outer first layer of finite elements. So these crosses are fixed nodes, they cannot move, and the points can virtually move in order to fulfill this relation between virtual change of the magnetic energy and force moving the body in a direction r. Okay, so the general expression now here, to be precise, is clear. We have to integrate h in dp from 0 to b, but remember we have to do this for these volumes here, so this layer of elements, and they are these elements here are within air. So we simply get here this relation. What we can use here simply that P is equal mu 0 h. That is why we get here now the first term here, which is b squared over 2 times mu 0. And here we have to take the virtual change in the position, so dr. And if you do this, this can be also written, as you know, as b squared. If you do here this virtual change, then we get here b in the virtual change of b with respect to r. This 2 cancels out with this 2, therefore we don't have this 1/2. And on the other hand, we also have a change on the volume. Therefore, we have a second term where we have this virtual change on the volume over which we integrate. This, as you can see, we have to take the sum over all elements we have within this layer around the body, and here integrate then over each of these element volumes omega e, which means that the force acting on the node, to get this, we have to take the sum over all the element nodes, which include here the node I. Therefore, we get here the force in r direction for this node, and we have here this term to be evaluated. Which also means, if we go back, if we have here such an element here, this node, and want to get the total force on this node by this principle of virtual displacement, this and this element will be involved. If we look at such a corner node, then these 3 elements will be involved. The same you can clearly do also when you have edge finite elements. Yeah, then we look here along the edges. Okay, so this is a second possibility, which is also quite accurate because we can express this virtual change of P and the virtual change of the omega analytically and then evaluate the whole formula numerically. Okay, so what is now our coupled system? And I have written this down here for the mechanical equation already in the semi-discrete Galerkin formulation. So we have here the inertia term with the mass matrix where the density of the body enters and the acceleration. A dot means a time derivative, double dot second time derivative. A damping matrix with the velocities at time step n plus 1. And here we have the stiffness matrix, and that clearly can depend on the displacement itself. If you have a nonlinear material relation, or you have to take into account large deformation stresses, strains, called geometric nonlinearity within mechanics. And the fourth term, which depends on the electromagnetic forces and therefore depend on the magnetic vector potential as well as its time derivative. And you see I've put it on the left-hand side because it is not known in advance. The second equation is our standard equation we have for electromagnetics, taking into account that we have moving deforming bodies. Therefore, the mass matrix depends on the actual deformation, on the actual displacement. We know we have to compute it on the deformed structure. Also, the stiffness matrix that also may depend on the vector potential here due to the non-linearity between B and H. So our magnetic permeability depending on the magnetic field. And we have the right-hand side, which are, for example, any conductors carrying currents. And they may also depend here on displacement or velocity because they can also be deformed by the electromagnetic forces or move in this sense. And may also depend on the vector potential when we have any permanent magnets. Okay, so you see this is fully coupled in this sense. We cannot solve it directly, but the main approach is to solve it iteratively, which means we first will solve here the magnetic equation, assume a fixed deformed state, get the new magnetic field. For this, we then can compute the electromagnetic forces. Knowing the magnetic forces, we can then solve this equation for the mechanical displacement U. And that we have to do iteratively between the two equation systems. And as a stopping criterion, clearly can be used the change of the mechanical displacement at the current time step we compute n+1 between iteration k and iteration k plus 1. Yeah, so this is the outer coupling loop between which couples the two partial differential equations. In a relative sense, we take the L2 norm, and if this is smaller than something like 10 to the power of -3, that should be enough. You can assume that you are converged and you can go to the next time step. This is also shown here schematically. So we have here the solution for the magnetic field with the inner iteration loop, because we may have to take into account the nonlinearity, which is the magnetic permeability. And we have the solution process for the mechanical field, where we assume that we now know the magnetic forces and we solve it for the mechanical field that also have an inner loop, because when we take into account any mechanical nonlinearities. And that is the outer loop, so I should write it here. So this is the outer iteration between the two physical systems, and we have denoted this with the iteration counter K. So when we have a new mechanical field, we have the new mechanical displacements, we update the geometry or update the computational mesh by this moving mesh technique, compute again the magnetic field, get new magnetic forces, and then go again and compute the mechanical field. And as we have seen as a stopping criterion, this makes sense. A second stopping criterion could be also that we use, instead of the displacement, the electromagnetic forces here. And clearly, if we have no change of the electromagnetic forces between two iterations, so between iteration k plus 1 and k, we cannot have any further change in the mechanical deformation. Okay, so you see, for magnetomechanical system, mainly you use this iterative coupling. Clearly, when you look here at this coupled system, you could also derive a Newton iterative scheme and solve this in ones. But for most cases, you are more efficient when you solve it iteratively, as shown here. But don't forget that you also check your stopping criterion via the change of the displacement between two outer iteration loops, or use the change of the electromagnetic forces. And when you fulfill such a criterion, then you can go to the next time step and again solve the iteratively both physical fields. So these are the general approaches, because what we see is that for magnetomechanical system, our coupling terms are nonlinear. So even if here we neglect the nonlinearities within our system matrices, we will have a coupling according to the electromagnetic forces, which are nonlinear, and in this sense, the iterative coupling is in most cases more efficient, but always taking into account clearly also the iteration within each time step to get a converged solution.